So thank you for the introduction. I am happy to talk to you today about our quantum cryptography educational kit. But before getting into the specifics, I would like to thank our collaborator Jörn Schneider, who is a teacher in Germany, and he's very enthusiastic about teaching quantum mechanics and quantum optics in general. And we developed this kit together with him, and it has been quite successful. As you can see here on the right, it made the cover of a German teaching magazine. And on that note, we're always looking for collaborators. So if you either have an experiment that you've already developed that is working nicely, or you have a concept that you feel is interesting, just get in touch and we'll talk about it. Okay, so let's talk a little bit about encryption in general. So let's say you either have a string encoded in bits or an image, and what you do is you have some sort of key, and then you do a bitwise addition of the key onto your image, which gives you an encoded image, and another bitwise addition of the key brings you back to your original image. Now you may ask yourself, in theory, is it even possible to have safe communication, right? Because that's the feature of quantum cryptography, is that you have safe communication. And you may ask yourself, is it in theory even possible? And the answer is yes. For example, using the so-called one-time pad. The one-time pad requires 3 prerequisites. First, the key is secret, meaning that it is only known by sender and receiver. Obviously, if a third party has knowledge of the key, that's difficult in terms of security. Second, the key is only used once and it is long enough. That's sort of easy to understand, because if your key is not long enough to encrypt your entire message, that's a problem, obviously. And if you're using your key several times, you open up your key to attacks such as a statistical analysis. So obviously you only want to use your key once if you want your communication to be safe. And thirdly, your key is completely random. Now this may come to you on first sight as a bit of a surprise, but think about how complex keys are normally generated. There are different methods out there, obviously, but think about, for example, the Enigma. That was a very, very complex mechanical way of creating an encryption key, but once you had possession of the mechanical machine and the underlying mechanism of generating the key, you could understand, or you could break the key. Now, when the key is completely random, obviously that's not possible, because there's no way to attack a random key. So this is why this is a prerequisite that helps to get towards safe communication. And you may ask yourself at this point, well, where does the quantum physics come in? It comes in 2 of those. The first one, that the fact that the key is only or should only be known to the sender and the receiver, this is achieved by the so-called BB84 protocol. This is what we're going to discuss on the next slides. And when we're talking about randomness, well, this is obviously something that quantum mechanics can help with, because there are certain processes that are random. Now let's look at the BB84 protocol. So first of all, we are going to use a notation that is often found in literature. So we're going to call our sender Alice and our receiver Bob. And the main thing to understand about the BB84 is that the 2 of them generate a tap-proof key together. And this process of generating the key, that is what makes it tap-proof. We're going to get into detail later. There's going to be a third party, namely Eve, which is short for eavesdropping. So she will try to intercept the the key generation or the data transmission between Alice and Bob, and we will see that her presence automatically leads to a trace that can be detected by Alice and Bob. So whatever Eve does, by the way that the BB84 is designed, she will leave a trace that automatically gets her detected. Now, once you have this tap-proof key, it's not surprising that you can transmit the encrypted message publicly, right? So if we have fulfilled all the prerequisites that I talked about, then we now have an encrypted message with a key that is completely random, that is secret, meaning only known to Alice and Bob. So if these prerequisites are fulfilled, then there's absolutely no information that can be taken from the encrypted message. Hence, it can be sent publicly. And finally, the way that Alice and Bob exchange information, exchange bits, that is encoded in the polarization state of the light that is used, namely in single photons. And what I'm going to show you is that our kit does not use single photons, and I'm going to talk about the relationship between classical and quantum mechanical aspects and how this feeds back into the teaching with this kit. That's something I'm going to discuss in a later slide. Now, the great thing about our setup is that you can play through all steps of the BB84 protocol. And so you see the setup here. It's comprised of 3 parties. We have one breadboard for the sender Alice, we have one breadboard for Bob, and you can put an eavesdropping unit Eve here in between the two. And you can, as I said, go through all of these steps. So first of all, you prepare the polarization state of the light that you want to send. Then Alice and Bob generate a key together. Obviously you can transmit data then, and then this is sort of the highlight of the entire thing. You can drop in the eavesdropping unit in between Alice and Bob, and you can really see and understand how her presence alters the measurement and gets her detected. Now I'm going to show you how our setup works and then talk about the BB84 protocol, because it will make most sense this way. So let's start out by Alice. So Alice is essentially a laser on a breadboard with a half-wave plate. The laser is linearly polarized, and if you push the red button here of the laser electrometers for 2 seconds, you will have a continuous wave laser, which helps you in aligning the system. And if you only push it down once, it will emit a short pulse of about 50 microseconds in length. So this is sort of our single photon. So obviously, as you see, the second you see the laser here, you are aware that our educational kit is an analogy kit, meaning that we do not deal with single photons, we only deal with short laser pulses. This means that this is not a true quantum optics kit, but as I will explain later on, there are a huge number of parallels which makes it really meaningful to teach in this sort of way by doing the short laser pulses. Obviously, you have to explain the differences to your students, and this is something that I will also talk about later on. So the half-wave plate here allows you to set a certain polarization orientation, so to set a certain state. And it's not apparent why that is at first, but I'm going to show you here. The half-wave plate will be oriented such that it has 2 different states in 2 different bases. So we're always going to look at 2 different bases, the x basis and the plus basis. The x basis is defined as the two states of minus 45 degree polarization and 45 degrees, being a digital 0 or 1. And in the plus spaces, we're having the polarizations of 0 degree and 90 degrees corresponding to a 0 and a 1. All of these polarizations are referred to as towards the orientation of the breadboard, or vertical and horizontal. So this is Alice. Then let's have a look at Bob. Bob similarly features a half-wave plate. I'm going to explain what that does in a second. The light then goes towards a polarizing beam splitter, and then the light can either be transmitted towards a photodetector or reflected towards another photodetector. And the half-wave plate decides whether it's transmitted or reflected, and then we just call the the transmitted path is called a 0 and the reflected path is called a 1. Now the half-wave plate only has two settings, 0 degrees or 45 degrees. This is equivalent to the choice of the measurement basis. So if I'm choosing 0 degrees, then but Bob is measuring in the plus basis. If Bob chooses 45 degrees, then he measures in the x basis. You may have seen it already here, but I have a larger image down here. So these photodetectors, they feature an LED at the top, and this LED signals where the laser pulse is detected. So either if you're transmitting, it will this one will light up, or if it's reflecting, this one will light up. And the reason we chose that is because we felt it's important to have sort of visual feedback. Of course, they could be hooked up to an oscilloscope or some other electronics on the PC, but we felt like it was actually more helpful to visually see, okay, this is where the photon, so to say, is detected. Now let's go through a couple of examples. So you place Alice and Bob opposite to each other, you adjust the laser such that it hits the apertures of the photodetectors, and now let's assume that Alice sends a digital 0 in the plus spaces. This corresponds to a 0 degree orientation of the half-wave plate, or of the polarization light that comes from Alice towards Bob. When Bob measures in the same basis, meaning he leaves his in the plus basis, he leaves his half-wave plate at 0 degrees, then the light will come in and this LED here will light up, meaning that the photon, so to speak, was detected here. Now, when we're looking at a different case, we want to send in the x basis a digital 1, then the orientation is 45 degrees here, so you rotate the half-wave plate in this rotation mount. Again, you press the button to send a laser pulse. When Bob measures in the x basis as well, then the light will go towards this detector and this one will light up. Now the third case is where it gets interesting actually. Assume that Alice still wants to send a 1 in the x basis, but Bob measures in the plus basis. And now the question is, what happens here? In the single photon case, a photon would arrive here with a 45 degree orientation on this polarizing beam splitter, which lets 0 degrees transmit and 90 degrees is reflected polarization wise. Now the 45 degree orientation photon comes in here, and what happens in the single photon case is that the photon decides at random which way it's going to take. Now obviously in our setup we have the problem that we are dealing with laser pulses. So the intensity of the laser pulse is split in half then. This would mean that both of the LEDs light up, which obviously would be a problem for this analogy experiment. So what we did in order to keep this randomness alive that the single photon would see, we integrated a random mode in this sensor electronics box here, which means that the sensor electronics box sees, okay, there's equal intensity coming onto those photodiodes here. This means we are in a state where the bases don't match. This means, okay, I'm going to light up one or the other LED at random. So this is going to be a random result here, either the one or the other will light up. Okay, so let me go over to the setup and demonstrate those different cases to you. So first of all, when I press the laser electronics button for 2 seconds, then the continuous wave mode is on. So the laser stays on. This is the mode of operation to align the system, which obviously we've done beforehand. Now, when I push the button now, only shortly, then you can see a little pulse. And this is something that's really hard to capture here on camera, so you're not really seeing it, but you can clearly see it when you're in the lab, so it's a short laser pulse. Now first, let's go through the cases. Alice here will start with her 0 in the plus basis, so that's a 0 degree setting for the half-wave plate. Bob is supposed to measure in the plus basis, so he's also setting his half-wave plate to 0 degrees. Now let's say I'm sending a photon or laser pulse, and you can see here, okay, this LED here lights up. So this is the indication, okay, Bob is measuring a 0. Now in the next case, Alice wants to send a 1 in the X basis, which is a 45 degree orientation, and as you can see here, the rotation mounts already have those labelings to make it easier for the students. And Bob also measures in the X basis, so he chooses the 45 degree orientation. And now when I send a pulse, then the 1 LED should light up. Yes, and it does. It's a little hard to see, but again, it's just from the camera, you can clearly see it when you're sitting next to it. Now, those are the cases when the bases match. Now let's look at a case where the bases do not match. So this one here is now measuring, so Alice is sending a 1 in the X basis, and Bob is measuring in the plus basis. So I'm rotating this to 0 degrees. Nope, 0 degrees. And so their bases do not match. And what we're going to see is what I've explained to you, that the result is random, so either of those LEDs is going to light up. And I'm pressing the button now, and you see the 1 is lighting up. Again, the 1 is just random. Okay, and so there's now the 0. Again, the 1. So you see, this is the random result that's happening when the bases do not match. Okay, so let's go back to the presentation. And now I would like to go into detail. So now that I've shown you the setup, I would like to get into detail of what the BB84 does and how this is reproduced in our setup. Because at this point, really, I didn't really explain to you anything about these 3 prerequisites that I talked about at the beginning from the one-time pad. So now I want to actually get into this and demonstrate to you how this key is generated. First of all, in order to generate this key with Bob, Alice chooses random bases and bits. So it's like a little table here where we're just assuming for no particular reason that there's 18 measurements, and Alice is going to fill this table before anything happens. So she's going to write down bases, and she's going to write down bits. And here comes the part where we said that quantum physics help, because we need random bases and bits. Now, this is a nice educational opportunity. When you're doing this with students, I encourage you to ask your students to write down in the PC like 100 or 200 digit long series of zeros and ones, and tell them that they are supposed to be completely random. And what you do then is you make an analysis how long the strings of, for example, ones are. So you count how many strings of length 1 there is, you count how many strings of length 2, so 2 ones after another, you count how many, and then you can easily see that the that a normal person is a very, very bad random number generator. So this is something that you can experience with your students firsthand by just showing them they can don't really achieve a good result. And actually what we do, or what we've done in the past in lab courses, in order to have random bases and bits here, we just gave them a box with 20 dices and just told them to shake the box, and then, you know, an even number on the dice is, for example, a 0, an uneven number is a 1, and the same for the bases. In terms of true randomness, you may or may not be aware of it, but you can actually buy quantum mechanically generated random numbers. So you can buy little boxes that will output you just a number of ones and zeros generated by a quantum mechanical process. So this is something that you can buy off the shelf. So this is where the randomness comes into play that I mentioned at the beginning. This is the choice of the bases and bits for Alice. Similarly, Bob also makes random choices for his bases. So he also fills this table here, but only for the bases. And what happens now is the two go through this measurement, meaning that Alice now, for the first measurement, sets her polarization state so that it matches the X bases and sends a digital 1, meaning a 45-degree orientation. And Bob sets his receiving unit to measure in the plus bases. Now, as I've told you, if the bases don't match, like in this first case here, where Alice sends in the X bases and Bob measures in the plus bases, the result will be random. So it could be a 1, like Alice sent, but it could also be a 0. Now let's look at the second case. Alice sends in the X bases a 0, and Bob measures in the X bases. And then he will automatically get a 0, right? Because Alice sends a 0, they both send and measure in the same bases. So if everything's properly aligned, there's no way to get something else than a 0. And they do that now for all the different measurements. So let's look at measurement number 3, bases don't match, random result. Measurement number 4, bases match, so he has to get a 1 because Alice sent a 1. Similarly for 5, similarly for 6, he will have to get a 0, same bases. And now, after one another, they fill this table. This is what the students would do, but this is, as I said, this is what the BB84 does. Now that I've done all that, there's another step where Alice and Bob compare not the results, but the bases they used for their measurement. And they can actually do that through a public channel. I'm going to explain why that is in a second, but let's just first do that. So it's literally like as if Alice would pick up the phone, call Bob and say, Bob, in my first measurement, I used the X bases. What do you have? And Bob says, well, in my first measurement, I used the plus bases. Now, what is the information that the two have now shared? They both now know that their bases don't match. So they know that the result for Bob is random, meaning that for them the measurement is not helpful at all. So they discard this first measurement. They go to the second measurement, and Alice says, for my second measurement, I used the X basis. And Bob is going to answer, I also used the X basis for my measurement. Or sorry, Alice says she sends it in the X basis, and Bob measures it in the X basis. Now what has happened now? Now they both know that they use the same basis. Alice knows what she has sent, and Bob knows what he has received, and they know for a fact that the two of those are identical. As I said, they share the information about the base publicly. Now, is that an information that is helpful to anyone? No, because no one knows the bit that Alice sent and no one knows the bit that Bob received. So from the information of the basis of the measurement afterwards, there's nothing that you can take from that information. So they now go through all those measurements. So as I said, if the bases are identical, they keep the bit. If the bases are not identical, they discard the bit. So we already said measurement number 2 is what they keep. Measurement number 3, not matching bases. Measurement 3 is discarded. Measurement 4, bases match, so they both mark this measurement. Similarly for 5, similarly for 6, 7 is also the same, even 8. Oh, measurement 9, so there is no matching basis. Measurement is dropped. Same for 10. 11 has the same basis, and so on. And now when you're looking at the numbers down here, you see that those numbers for the bits are identical. So that has to be the case, obviously, because if they choose the same basis for each measurement, then they have the same result, or more precisely, Bob measures what Alice has sent. There's no way around that. So this is how they have generated the key. So these numbers down here are the key. So 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is how the two of them generate the key together. They choose their bases at random. Alice chooses bits at random. She sends them. Then they do this round of telling each other what their basis for their measurement was. And then they both know which bits they're talking about, even though they never talked about the bits. They just talked about the basis. And now that I have my key, I can obviously encrypt my message, send a message, decrypt it, and be happy about it. Okay, so this is how the BB48, no, BB84 works. But the major advantage, or what makes the BB84 so powerful, is what happens when somebody's eavesdropping. So that's the highlight, obviously, also in the lab course, to introduce Eve. So we're putting in this eavesdropping unit, and when you're looking closely, you see that this unit here is comprised of one measurement unit, so to say. So it's the same that Bob had. So we have a half-wave plate to choose the measurement basis. We have our polarizing beam splitter and the two detectors. And once Eve has done the measurement, she will try to relay that information and just pass on another pulse or another photon with the state that she has measured here. And, well, the fact that Eve can be detected obviously is based on the fact that every measurement will alter somehow your quantum mechanical state, right? So this is what we're using, and I'm going to show you in particular how this is done. So first of all, let's assume that Alice and Bob measure in a different basis. Let's say she she sends a message or bit in the plus basis, and Bob measures in X. Now, regardless of what Eve does in the middle, this case is not super interesting because, as I told you before, when the two bases of Alice and Bob don't match, then they discard this particular measurement anyway. So that's not an interesting case. It's more interesting when all of the three choose the same bases. So let's look at this. Just assume that Alice wants to send a digital 1 in the X basis, which means that she's going to send a photon or laser pulse at 45-degree orientation. When Eve chooses the same basis for measurement, then she's going to get the 45-degree orientation, meaning that the detector here will light up. So she says, okay, I measure a digital 1 in the X basis, and that's what I'm going to send, right? So 1 in the X basis. So she's going to send a photon with 45-degree orientation, and when Bob measures in the same basis, well, then he gets the 45-degree and measures in this basis and gets the digital 1. So through all those steps, Alice sent a 1 and Bob received a 1. So no one actually realized that Eve is in the middle, right? So for this particular case, when all of their bases match, then Eve's presence is not detected for this particular bit. Now let's look at the only remaining option, that Eve measures in a different basis than Alice and Bob. So let's look at it again. We have the same state that Alice wants to send. Now we said Eve measures in a different basis, so she measures in the plus basis. And as we said before, when the bases don't match, the result of the measurement is random. So it could be that she measures a 1. It could be that she measures a 0. Let's assume it's a 0. It doesn't matter for this particular example. Let's just assume it's a 0. When she's done that, she's going to try to relay that information. So she's going to send what she has measured before, which is the 0, and she's going to send it in the same basis that she has measured in. So she sends a 0-degree polarized photon. Bob, as we said, it's only interesting if he has the same basis as Alice, because other measurements will be discarded. So he measures in the X basis. And again, it's random what comes out of this measurement, because Alice sends in plus, he measures in X, so the result is sort of random. Now, it could be that he measures a 1. In this case, again, Eve would not be detected because Alice sends a 1 and he receives a 1 in the same basis. But the fun part is when he actually measures 0, right? So in half of the cases, when Alice sends it in a basis that doesn't match, he's going to measure a 0. And that's an interesting case now. This is the case where Eve is detected. So Alice is sending a 1 in the X basis, and even though Bob is measuring in the X basis, he receives a 0. So even though the bases matched, the results did not. And now you're maybe going to say, oh wait, but you told me a couple of minutes ago that they only compare the bases and not the bits. Well, this is something that they actually do, in fact. So after generating a long key, they will compare a number of test bits. And this is where they then know, okay, somebody listened in on us, because when you do the math and go through all those states, then you will see that 25% of the cases will feature a false test bit. So this is really where you know, okay, someone listened in on the key generation. And I'm choosing my words carefully here. Someone listened in on the key generation. So it's not like 25% of the message bits were recorded by Eve, but instead it's in the key generation process. So all of this happens before the actual message is encrypted and sent, right? This is important because obviously if 25% of the message would be intercepted by Eve or decrypted by Eve, that's a real problem, but this is not the case. So we're only talking about the key generation protocol. And when Alice and Bob compare their test bits and there are no mistakes, then they know, all right, no one listened in on us. And when they compare the test bits and they do find about 25% of false bits, then they won't even proceed to encrypting the message and sending the message, because in the step of the key generation they already recognize, okay, something's wrong here. And now I'm going to show you the case in the experiment where this where I can actually see this. Okay, so again, let's go to the setup. A colleague was so kind to align the system while I was speaking. So we dropped an Eve here in the middle, and we're going to demonstrate now the case where Eve is discovered. So as I said, this is when the bases don't match. We start out by setting Alice to the X basis, so 45 degrees, meaning she will send a digital 1 in the X basis. Bob also chooses the X basis, meaning his half-wave plate is set to 45 degrees. Okay. Now, as I said, Eve, for the case, in the interesting case is when Eve has a basis that does not match, meaning we have a 0-degree orientation of the half-wave plate. So Alice and Bob measure in the X basis, Eve measures in the plus basis. The result will be random. Let's see what happens. Okay, so the LED of the detector 1 lit up. And now we will forward what we measured. So we have to use a digital 1 in the plus basis, and that corresponds to a 90-degree setting of the half-wave plate. So as I said, Eve tries to forward the information that she measured. She measured a 1 in the plus basis, and now let's see what happens. The bases don't match, so the result will be random, and the 1 lights up, the 0 lights up, just showing you the different cases here. The 0 lights up, the 1. So this is the random result that I was talking about. And now when the 1 lights up, then Eve is not detected, right? Because Alice sent a 1 and Bob detects 1. But the case with the 0, that's the interesting part. So when the 0 lights up, then this is the case where, although Alice and Bob have the same basis, their bit is different. And this is what's going to reveal Eve's presence. This is what I promised you to talk about. So we should talk about quantum versus classical. And I think it's really important that when you work with a setup, you discuss that with your students. It's important really to point that out. This is a classical experiment. Everything that you have on the table here is classical. But it's a really nice way of teaching about quantum optics. Now again, to point out the differences, in our setup, 1 laser pulse carries 1 bit of information, meaning that a huge number of photons carry the same bit. In contrast, in the BB84, only 1 photon is supposed to carry the bit. Now why is that? If you're having several photons, then Eve could perform measurements on those photons, reconstruct the complete quantum mechanical state, and then pass that on to Bob. If you're only having 1 photon, then this reconstruction of the complete quantum state is forbidden by the no cloning theorem. because the no cloning theorem states exactly that. So you cannot make a one-to-one copy of the same quantum object with all the identical states, because if you could do that, you could just copy or clone your photon that carries the bit several times and do your measurement with the clones and then fully determine the quantum state, but that's not possible. So this is why one photon only carries one bit. The next thing is where classical and quantum do not match in this experiment, is that if I'm having a single photon and it comes to a beam splitter, to a polarizing beam splitter with 45-degree orientation, there will be true randomness. So if it's transmitted or reflected for the single photon is a random process. Obviously when you're doing statistics it's going to be 50-50, but for the single photon it's going to be random. This is something that we implemented in our electronics. So when you're having the laser pulse and the two intensities here match on the photodiodes, the sensor electronics will tell you, okay, I understand that I'm supposed to output a random result now. And once the students have understood that, they can still comfortably play through all of the BB84, and this is the point of this whole experiment, so that you can have something to work with, to have something in your hands that enables you to understand all those different steps. Because obviously you can go to a blackboard and write all those zeros and ones down, but I'm very confident that the rate of understanding for students is going to be a lot higher when they can sort of go through this process with their hands and see what Alice, Bob, and Eve are doing and how this key is generated amongst them. Now you may ask yourself, well, why don't I just build a quantum system that does the same thing? And the answer is you certainly can. The problem is that what you're going to have to put on your table will bring you in the range of a 5-digit number, and there's probably going to be a 2 or a 3 in the first digit. So it's just very expensive, and not too many schools can afford a true quantum optical setup where they can demonstrate the BB84. So this analogy kit is a way of enabling you to teach about it, because students are quite enthusiastic to learn. And I have an example from a university in Germany where the lab course leader actually has a dedicated room where students can go and perform experiments when they have finished their normal lab exercises. And in this room there's a couple of exciting experiments, and he bought 2 of those quantum crypto kits, and the feedback was that this is always packed. So this is always the setup that students go to first, simply because quantum cryptography is a topic that you hear about a lot, but few people have a working understanding of what the actual process is and how this safe nature of quantum cryptography and quantum communication is achieved. But finally, I want to answer 2 frequently asked questions that I get when I talk about this. So the first one is, does quantum cryptography require polarization entanglement? So this is something that people come up to me and say, hey, what you're doing with your kit is cool, but aren't you missing out on the entanglement? And the answer is no. So yes, there are protocols that use polarization entanglement, but the BB84 does not. And you can actually see that simply by the years of the publication for those different protocols. So the BB84 was published in 1984, hence the name. And in the protocol, polarization entanglement is not mentioned. And the papers that set up protocols with polarization entanglement were published in the years after. So yes, you can do it with entanglement, but it's not required. The second one is, and this is something that I get from students a lot, so how does quantum crypto work when you're really looking at a practical result, because they're going to say, okay, now we learned that ideally one bit is carried by one photon, and then they're going to recall that in the news, for example, 1 or 2 years ago, there was report of an experiment done from a satellite, where a satellite communicated with a station on Earth with quantum cryptography. And now they say, okay, if one photon carries one bit, this poor photon will have to go through so many kilometers of air where it can scatter, where it can get absorbed by the air itself or by any particles in the air. And even if you're choosing a nice wavelength for that, there's still going to be quite a good number of photons lost. How does this work? I'm not going to go into detail here, mainly because I'm not the expert on those, but if you want to read up on how this actually works, then the term you want to read up on is decoy states. So this is how it's done in practice, because it wouldn't be practical to actually send one bit per photon, so it's done a little bit differently, and this would be the term to look up on. So thank you very much for listening in, and I'm happy to answer any questions that you may have.